Okay, folks, welcome back. It's the time for the second lecture on economic integration in the European context. European integration is a course you came to last week. I hope you came to the review section with Berfin, and we'll see how that goes over time. This is review for a lot of people. So many of you have taken Macro 1. This won't be too difficult, but maybe you haven't seen it through this lens before. We'll try to do a little bit less theory and more applied thinking about this model. So to get going, let's review last time. It's a tradition with me. I always maybe spend about 5 minutes talking about what we did last time to remind you, put everything in context. We'll talk about the Solow Model, which is one of the foundations of macroeconomics. It's used in undergraduate and graduate teaching around the world. It has its limitations. A lot of people would criticize it for just focusing on economic growth as being something that we're going to continue to have. We can talk about that at the end of the class, maybe, if you're interested. I'm open to any interesting modifications. I'm actually doing some research on this myself, how to think of the Solow model if we have to deal with an upper bound on economic activity or upper bound on the accumulated carbon dioxide emissions we have in the atmosphere. These are things that can be done with the Solow model. It's an incredibly flexible setup. That's what makes it so exciting, because it reduces the action of macro to a few key variables. One is capital per capita. Capital meaning not just a machine, but the building we're standing in right now, the highway we have, all the rest. So how do we get capital? How do we accumulate? That's the lesson of the Solow model, is that it has to be done by deferring consumption. By not consuming is the way to accumulate. So if you want to grow like the big guys, you have to accumulate capital. You have to forsake consumption in the short run. And we've seen that countries like China and Vietnam have actually been able to do this. A better example even is South Korea in the decades starting with 1970. You know, these are really interesting examples. Other countries don't do it. The question is why. So these are things we have to deal with. So we'll have why is this relevant for European integration? Well, it has to do with regions also obeying kind of their version of the Solow model. You can imagine that when a country doesn't allow foreigners to come in and put capital in their region or their country, then this means that you have to do it yourself. So what is that benchmark about? That's what this Solow model is going to give us. And then I'm going to give you some of the limitations of the Solow model. So why is it a good setup for understanding economic growth, and where can it fail? Really important. And you learned this probably in your Macro 1 course with me or with Professor Weinke. Okay? So last time we talked about European integration, very broad brushstroke lecture. We talked about sort of the challenges facing Europe after hundreds of years of war and conflict. Maybe economic integration could be a secret to achieving some sort of peace and political integration and maybe even prosperity. And if that's the case, we have a lot of things to think about. What makes European integration happen? So I gave you lots of contexts, and I really urge you to look at the first chapter of the book by Baldwin and Wiplows. It's really a great introduction to the European situation. I mean, it's a wonderful book for non-Europeans, but every European should kind of have this in the back of their head. This is your starting position. You have to deal with this. You know, you can't change history. That's the terrible thing about history, is you can't change it. You can only learn from it. And then I gave you this wonderful way of thinking about the factors of production in Europe, because the factors of production is what makes us rich. If we want to be well off, we're going to have people work. People have to work. You have to have people, and they have to want to work. That's part of the story. The other part is they have to have machines and equipment and capital to work with. So those two ingredients are kind of the basis for prosperity, and then the rest is how do we allocate it? And that's why European integration, in my sort of context, is trying to achieve that efficient level of integration in some way. And focusing on that Edgeworth box gives us a great way of thinking about that. Okay? How can we put capital and labor in a unified region to its best use. That's really what it's all about. Okay? So in Berfin's section, you repeated what we did before, focusing on the first idea of integration, namely efficiency. How can we achieve the best outcome? When I say best, it doesn't necessarily mean the most cars. It could be the most anything, but doing the best we can given the resources we have. You can also use resources to produce good health care. You can produce good environmental protection. So it's really not just about material consumption. Now you can contrast that with fairness, just everybody having the same income. That's another type of outcome that people might want to have, but it has nothing to do with efficiency necessarily. Okay, really, we have to think about, first let's try to make the cake as big as possible and then divide it up in a way that makes us feel like we're going to be able to perpetuate the system, or be able to incentivize people to do the necessary work and savings and investment to make this outcome possible in the long run. Okay? We started with this single good, two factors of production. So it gives you a perfect example of how to think about the production function. And then if you have capital and labor, you can have it in region A or region B. Today we'll talk about Finland versus Poland. Finland is rich, Poland is kind of poor. They come together and they start interacting in some way. Again, efficiency is coming through the Edgeworth box in the sense that if both regions have the same production function, then the tangencies of the isoquants using the factors of production either in region A or region B are going to give you a diagonal. The diagonal solution is kind of an important outcome. And it may disturb some of you to think about that, but if you think about France and Germany, they're really quite integrated. And they have almost identical capital-labor ratios. If you do the calculation with some sort of adjustment for certain types of output, services versus manufacturing, France and Germany are really well-integrated economies. So they've achieved kind of through these mechanisms the efficient outcome. And that modified Edgeworth box gives us a way of thinking about that, just a way of applying our economic knowledge. And I'm going to take this very neutral, think of Poland and Finland after the Iron Curtain fell and people were free to move, capital was free to move. Poland and Finland were kind of market economies. This is a great metaphor for the entire East-West situation. So we're trying to give this just as an example. So don't take me too literally. And again, we'll see later when we talk about trade, you can trade with third parties. Right? So it's not just Poland and Finland, but it's Poland and Finland in the context of the world economy. Right? That's the way I wanted you to think about it. And that's why this box is kind of important, because it's going to kind of summarize all those ideas. On the horizontal and the vertical axes, we have labor and capital. Those are the factors of production. Remember, if you want to be rich, if you want to produce output or just make people healthy, you need capital and labor. So that's the fundamental assumption, is that this stuff is there. And the question is, how do you allocate it across two regions? And that's where the regional integration aspect comes from. So we talked about 4 different mechanisms. We talked about internal capital accumulation. That's my goal today. We also talked about capital mobility. We talked about labor mobility. And we talked about regional trade. So those are the 4 mechanisms, the big 4, that will make this course sort of gel for you. But of course, there's a lot more to that mechanism, this integration, than those 4 mechanisms. So again, being a good economist means to be able to think critically about it. Not just memorize it, but be able to think, hey, maybe there's more to this. What did I assume to get this result? That makes you an economist. So what do I need to assume to make this work? I need to have some view about how factors of production are converted in any process, but most importantly in a market process, into output. And there's only one output in this game right now. So we're going to think about a constant returns to scale production function with a kind of a GDP, a Hicks bundle, we called it in microeconomics. So it just frees the content of the bundle, the basket of goods, and the idea is we use capital and labor and some sort of technology which is given from above to deal with it. Okay, so the most general form would be the function f. A K, L. A is given, can't change it. K, we could move it around. L, we can move it around. Now, if you assume constant returns to scale, you already buy into that second line. Okay? I'm sure you saw this in micro. You saw it in my macro course. This means basically that if factors are paid the marginal product, then those two factors here exhaust the output. There's nothing left. There's no excess profits, right? So, and this is the magic of constant returns to scale production functions. The marginal product of capital times the input of capital plus the marginal product of labor times labor is equal to output. So this means basically it's always going to be a struggle between capital and labor, right? Even if capital is fairly compensated, even if you have perfect competition in the factor market for capital, it's always going to be kind of a trade-off. So keep that in mind. It's not a judgment, it's a fact. It's just a fact, right? So under our conditions, we thought about, okay, well, how can we do the best we can with these two regions integrating, Poland and Finland? What do we do? We already discovered last week that the diagonal was the efficient set of points. Okay, that's an easy one to understand. We can actually write down a mathematical problem with a Lagrange multiplier, and you can look at the first order conditions, and you can prove that. And I think Burda basically just showed you that the marginal products of those two uses of capital and labor will be equalized when you're on the diagonal. That's already kind of an informal assertion of efficiency. But you can do it more rigorously. If you like the math, you can set up the Lagrange problem. Okay, it's not incredibly difficult. But that set of efficient allocations is the logic that's going to guide us. If we're producing only one good, okay, we have to be on that diagonal. And just logically, Finland starts out the game with a high capital labor ratio, steep angle, and put yourself on your head and look down from Poland's position, rotate that position, Edgeworth box 180 degrees, put Poland in the lower left, and you see that Poland has the lower capital labor ratio. Okay, so that's the initial condition is something like point E. So that's the endowment. And the question is, if we want to think of European integration as making things more efficient, how do we get from E to some efficient allocation? Well, if there's only one good, we have to move to the diagonal. I'll show you later that if you have trade, you don't have to. You can trade to an efficient point without even moving E. But that's more advanced. Let's just stick with the first set of ideas. So anything that gets efficiency will be part of the European integration process. I'm going to start with the basic process today. So let's just suppose that point E is the endowment, and Finland doesn't want to give any capital to Poland. It doesn't want to do any FDI. Okay, so what happens? Well, then Poland is going to have to grow on its own. Poland is going to have to accumulate capital. So that Edgeworth box is no longer Edgeworth, it's a modified Edgeworth box because the height of the box will change. Accumulating capital means, well, where does it come from? It doesn't just fall from heaven, right? It's families save and invest beyond that which they need. Okay, so that's the first change of the Edgeworth box. Makes it a modified Edgeworth box. Okay, so you could imagine maybe some third country would throw some capital at this game, but that's not what we're talking about. We're talking about Poland pulling itself out of the swamp with its own bootstraps. Okay, so that this is what would happen under autarky. This is the benchmark for our whole analysis. Anything that Poland does should be at least as good as that. And we'll show today that that's a very slow process. So accumulation via Solow model is a slow process. It's a slow slog, and it makes people a little bit pessimistic. It's going to take a long time to converge. Okay? We learned last week, but we'll see in 1 week from now, that moving capital is another alternative. So people in Finland could put their trucks on a ship, send it to Poland, and they could put their trucks to work in Poland. Okay? Or they could put their cranes on a ship and ship it to Poland, which actually happened. In fact, you can even take a factory apart. If you have enough money to make it happen, you can take a factory apart and move it. And I've seen that happen between East and West Germany. between West Germany moving their machines and factories to East Germany. Okay, so that's another possibility. Or, easy, the Poles say, we'll go to the money, we'll go to where the capital is, and we'll work there, because the marginal product of labor, of my labor, is higher there. Right? So that's the other alternative. The sum of those two vectors will give us this integration process. Now, as I said already, the interesting thing you may not have seen in any of your courses, unless you took Professor Kamika's course, is that trade can also move us in an integrated direction. That's exciting, right? It means we don't have to move the Finns and the Poles. They can continue to speak their own language without any sort of feeling of insecurity. They can just stay where they are, but they have to produce the right stuff. Okay? Today we're going to focus on this one, because this is the one you've already seen in macro. You've maybe even seen it in some other course you've taken. Okay? So under autarky, the Poles have to do it on their own, and this is going to require the Solow model. The Solow model is explaining how countries grow, because Poland is poorer than Finland, because Poland has a lower capital labor ratio than Finland. The assumption is that Poland and Finland have equally intelligent people, equal capable people, equal endowments of human capital. Everything is the same except for this capital per capita. That's the driving force. And Solow tells us how this happens. He told us this a long time ago, more than 70 years ago. Okay? So we're kind of assuming that Finland is already kind of at a resting point. They've accumulated to the right position, and really it's all about Poland right now. So the rest of this lecture is going to be about how Poland can grow and how long it takes, and what kind of evidence do we have from the United States, Japan, Western Europe to see how quickly that happens. Okay? So what do we need to assume? A model always assumes a few things, and then we can challenge the assumptions later. We're going to assume that the people in a population of this region, Poland, it's growing at rate little n, and we're going to focus on outcomes where these people are all working. If they're not working, you can do things that can change that fraction of people working, but you can't do it forever. You can't achieve growth with that. You can achieve one-off changes. So we'll come back to that in a second. So let's assume that n people are working in this economy, and little n is the growth rate of that big N, and these people are working h hours per person, right? If you want, we could use L. You may use L in your notation. So L equals N, okay? This is called the full employment assumption. So what matters for production is labor input, not just a person standing there, but a person doing something. The number of hours worked, the extensive margin matters. You may have learned that in my class. Okay, so we'll basically assume that the labor input is equal to the number of people, just to keep track of things in an easy way. So we'll normalize everything. And again, as I said before, if you can mobilize the female population because they've been discriminated against or they've been treated badly, they can't have children and work at the same time, any way that you can improve that ratio is good, but it's not going to lead to growth. It's not going to lead to a change in the growth rate. What it's going to do is it's going to shift the amount of potential output per capita for any given number of people, right? That's basic. Okay, so if we do that, we can use this production function and start thinking about the Solow model, the same production function we used in the previous analysis. So again, I wrote it in a more specific way now, but again, A is like this technology that we don't really assume is different between Finland and Poland. Maybe it's different between Poland and Algeria. And maybe there are all sorts of reasons why that A would be different, but we're not going to talk about that today. We're just going to talk about common production function. What does it mean? So what do we need? We need properties. More people working, more labor input, more output. That's the first derivative. The second one is more capital makes us richer, right? And we have constant returns to scale, which means that if I take tau, just any constant that's positive, and I multiply it by K and L, I get tau times output I had before. It scales. We say it scales. That's a great concept, scaling. Getting big doesn't matter. Productivity of the inputs is the same. If we have that, we can make it intensive. So I can divide by anything I want. I'm going to divide by L because I care about per capita. So if I divide the left-hand side and the right-hand side by N, or by L, because they're the same, I get per capita. So I get per capita output, I get per capita capital input, and I get 1, which is constant. So I can throw it away. All that matters for the Solow model, holding A constant, is capital per worker. So if you come with me to Poland, we look at Polish factory, we'll see one thing is that their factories are more labor intensive than the German ones. They're making the same stuff, but they're using a lot more people. Another way of saying that in economics is that it's more labor intensive. Okay, and there may be reasons for that. Maybe the Poles are just approaching some German ideal, or maybe they're focusing on some other type of good, right? But in the case of the Solow model, it's very clear that output per capita is a function of capital per capita. So the magic of being a wealthy nation means, how do I accumulate to get lots of capital per capita? How do I build lots of highways? How do I build lots of hospitals, lots of schools, lots of production facilities, drive lots of cars? How do I have more environmentally friendly stuff? You know, all that can be thought of as a way of increasing capital per unit of labor. Now, the bad news is that this is a concave function. So boundless accumulation will not get you to nirvana. At some point, the scale takes over, because we have constant returns of scale in both factors, but if you keep increasing capital per unit of labor without increasing anything else, you're going to run into decreasing returns at the margin. Common concept in neoclassical economics. Mathematically, the first derivative is positive, the second derivative is negative. Okay? Basic stuff. Okay, so again, I like graphs. I like to do this. I like this, because this is what Solow did, and Solow, is the most widely cited article in economics, still after 75 plus years. So it must have been something in it. And it's still being used for all sorts of applications, including studying the environment, etc. So intensive form production function has this wonderful curvature. The more capital per capita we put in, the more we're getting per capita, but at a decreasing rate. The increments are decreasing. So at some point, I may be proud of all this capital per capita, but it may not be getting me very much. And the Solow model tells us exactly where we want to land. Okay? But again, let's summarize. The first conclusion is the wealth of nations is a function of capital per capita. And when I say wealth of nations, I don't mean just having a big GDP. The US has a big GDP, China has a big GDP, but what matters is GDP per capita. What is the potential that we can do with the GDP? And that's why it's not surprising that a country like Luxembourg or Switzerland or Norway is actually wealthier than the US, Germany, or China. So it's not just size that matters. And the second conclusion is that what matters is how, if I want to grow, I'm going to have to accumulate. So I'm going to have to not eat. I'm not going to be able to eat in the sense of consumption. And when I say eat, I mean like eating a car or eating all sorts of other stuff that I consume. Not consuming means I have resources for gross investment. Right? So this is really basic stuff, macro one, but people forget. People forget after one semester. I, investment, C plus I plus G plus X minus Z or Z, okay? So if you're a closed economy, it's C plus I plus G, and we're going to put the government on the side, so it's basically I versus C. A country that consumes a lot won't be investing very much. And if you think about it, in a lot of countries that are developing, you really want to look at C plus G, because a lot of what the government does is consumption. And they're redistributing, or they're, providing certain types of services. So the question for me is, why does an economy stop in the Solow model? And to understand that, we have to derive the Solow model. So I'll do it quickly. Berfin will do it again, and you should look at the book, look at the notes. We need to look at savings, because savings is the incremental addition, potential addition to the capital stock. If you want K to rise, you're going to have to make K grow beyond that which is needed for depreciation to replace the old stuff. And therefore, we have to ask the household that is doing the savings, either directly or indirectly through their corporations that they own, or possibly through the government that it controls. We're going to leave the government out of this right now. We're just going to look at the savings function of households. Now, Solow was genius because he said, look, I look at these data and I see that Germany is a number like 0.25 or 0.2 now, and the United States is more like 0.15. Now it's like 0.12, okay? But it's very steady. So why don't we just assume that the savings rate that households in the aggregate, maybe not you particular, but the aggregate household in the United States is about 0.15, and in Germany about 0.2. So just as a starting position, a constant savings rate. It's really easy. And Solow got a lot of credit for that, because he was the first one who was brave enough to do it. If you do that, then you see that the savings that an economy generates every period for potential investment in the capital stock has to be a fraction of GDP per capita. If you're looking at savings per capita, it's going to be little s times little y. Okay, so it's just easy math, super easy. And if you plot that, you got a new function here, which is the savings function. It's under the production function, intensive form. It's the savings function of the economy. And the residual, the distance between the top one, is consumption. And that's what makes us happy, or makes us healthy, whatever. So, if we're just saving to build more factories so we can produce more factories, that's not so great. Right? So really what we care about, Solow told us, was the upper bar, the difference between the production function and the savings function. And yet the savings function gives us the ability to produce in the future. Right? So again, the simple assumption of a constant savings rate gets us pretty far. So what do we do with the savings? Well, we're going to put it into this capital stock. Now, does that go for 1 for 1? Is that going to increase the capital stock 1 for 1? What do you think? So again, this is completely basic stuff. Yeah. Increasing the capital stock requires going beyond that of the capital stock that just falls apart every period. So I just bought a new coffee machine. Now, why did I do that? Because the old one just died. It was leaking, it wasn't working anymore. That's my capital stock. If I were actually using that coffee machine to sell coffee to people on the street, it would really be part of the German capital stock. But in a sense, to help you think about it, everything has wear and tear. Every factory sort of falls apart after a certain number of years. Maybe even after 7 or 10 years, you have to replace lots of stuff. Every truck starts to wear out after the first year. So just replacing the stuff that's worn out is already requiring your savings. So you got to replace that stuff. Basic stuff, basic logic. Think of my coffee machine, but really think about Germany replacing all the highways that get worn out every year because people drive on them a lot. Germans like to drive, right? That's the way it is. So the usage implies physical depreciation. So the capital stock is already going to be diminished by delta, this depreciation rate, which is applied to the whole K, capital K, not the small k, the big one. Okay, so that's a huge, if you look at the data, look at the GDP statistics of Germany, how much of German GDP, which is gross domestic product, goes to depreciation, just replacing the stuff that wore out last year. It's quite a bit. okay? And if you want to make little k grow, you're going to have to do better than that. You're going to have to replace that stuff, and you also have to worry about all those people that are coming on board. So I mean, you have n, and next year it's 1 plus little n times n. So you have more people. So if you want little k to grow, you're going to have to not just replace the stuff that wears out, but you're going to have to give the new n some k, right? So you're going to have to actually do better than just depreciation if you want the capital stock per capita to grow if the population is growing. Now you might say, well, in Germany, we don't have kids. Sorry, we have immigration. We have lots of immigration. And I think for economic purposes, if you just focus on that, it's a great thing. Okay, it gives us more factors of production. But you've got to give those people more capital. If you're losing people, like Japan, shrinking, you don't need as much investment. Fact, right? So keep that in mind. We need to think about capital per capita. So little delta k, or little k delta thereof, is a race between the numerator and the denominator. Right? The numerator is big K, and big K is shrinking by delta if we don't do anything at all. And then we got to give more capital because of all these new people. In a country in Africa, for example, where the birth rate might be, the natural birth rate might be 2% per annum, you need lots of capital just to stay put. Right? So this is, again, the dilemma of economic growth for countries that are trying to develop. So if we just put our thinking caps on and look at this ratio, it has to stop changing when the rate of growth of the numerator equals the rate of growth of the denominator. That's basic McKinsey mathematics, right? The ratio stays constant if the numerator and the denominator are growing at the same rate. Therefore, I look at the denominator and look at the numerator, and then I ask, okay, what's doing that? Well, the numerator we kind of know has to do with capital formation, and the denominator has to do with population growth. Okay, so if we don't, without doing anything else, the rate of growth of k has to be equal to n. This is basic stuff. So it's a race, but we still have to figure out what delta k is. Delta k is the change in the capital stock after the depreciation has been taken away. So it's going to be I, the gross savings of the households, minus the depreciation in every period. Again, a lot of economists know this, but many don't. There's a difference between a stock and a flow. When I'm talking about GDP, I'm talking about a flow. Capital stock is a stock, and that's why we say capital stock. So every period, every year, every quarter, there's this flow of increment to the gross capital stock, and there's this flow of loss through depreciation. So you have this, the change of the stock is a race between the flows in and out. Gross investment minus depreciation. Therefore, we have two races. We have a race between gross investment and depreciation in the numerator, and we also have the race between the numerator and the denominator with respect to capital and labor. So if we want this thing to stop changing, we really have to be investing enough to cover depreciation and population growth. Otherwise, capital stock will not be constant per capita. And that's why the first result of the Solow model is this one, the capital widening line. It's a straight line. If I have lots of capital per capita, I'm going to have to save a lot to keep the capital per capita from changing. Right? Why? Because I've got depreciation to keep up with and I've got population growth to keep up with. And that's delta plus n. Okay, but I already have a savings relationship. So if I want to find out why some countries stop here and some countries stop here, I need to know how much people are saving, and then I've got the Solow model. So I put A plus B together, and I get C. I've got a potential equilibrium where investment per capita is enough to cover what I need to keep capital per capita constant. It's really easy. So if you master this, you understand basically half of what macroeconomics is about. Because this is our bread and butter. How do we produce GDP? How you distribute it is another question. You want to do the best you can, but this is where it comes from. Everything else is figuring out what determines little s and what determines the production function. Okay? Now the Solow model is wonderful because you give me this machine, I can tell you lots of things. I can tell you lots of stories. One story is that countries that save a lot per capita with the same production function will be richer than countries that save less. So accumulation is kind of a source of GDP per capita. And we already knew that, but you can see this just by taking this example and asking what happens if we increase the savings rate. We call that comparative statics analysis in economics. Comparative statics, we compare two steady states, two outcomes by changing one parameter, and one parameter only, the savings rate. We know the Germans save more than the Americans, okay? So everything equal, the Germans should be richer than the Americans, right? Because if the Americans started saving more, that would mean there's more capital per capita that can be accumulated because suddenly this red line exceeds the capital widening line position at K star. So this cannot be an equilibrium. That red bar is going to be net capital accumulation in that instant. And if you start accumulating capital, then K star has to go into motion. It has to move to the right if it's positive. So suddenly, this is no longer an equilibrium. Delta K is positive. Therefore, we move in this direction. That's why I have these arrows here. You can see quite vividly that suddenly we now move to a new position. Y star is higher, more output per capita, more capital per capita. Okay, it's a basic result. Now you're going to say, well, I looked in the GDP statistics, and actually at current exchange rates, the Americans, the US has a higher GDP than Germany. How can that be? Well, you're assuming the same production function, and I'm assuming the same production function, but in fact, Americans work more than Germans. Fact, more hours per capita, so it's not a fair comparison. And maybe the production functions are not the same. And maybe Germany's a bit more regulated than the United States. These are all things that growth scientists, growth economists look at. Okay? There's all sorts of other things. You might say, well, the Americans have less health care, blah, blah, blah. Okay, these are all arguments that we can make. But in fact, this model produces a prediction, which is that countries that invest more should be richer and they should grow faster. Because we may observe a lot of countries that are in this process of moving from one place to another. We don't observe everyone in a steady state. So if you look at the data, you see that indeed countries that invest more per capita grow faster. Okay, that's a fact taken over many, many years. This is an old picture from one of the editions of my textbook. It just kind of shows you there's a positive relationship. It's not perfect, but there's something to it. So the growth miracle of China, Korea, Vietnam has been accompanied by lots of investment. Fact. Okay? Within Europe, Poland, growth miracle, lots of investment. A lot of investment came from somewhere else, but in the Solow model, it's coming from you, the households. Okay, so that's a start. That's a start. We're not done yet, but we can already see this as a powerful tool. We can understand how European integration might occur even without any sort of movement of factors. Maybe just Poland accumulates over time and becomes more like Finland, right? Well, Solow in this form is baby version is just too easy and it's not really enough. Why? Because when you reach that Y star, you're not growing anymore. Per capita GDP is constant, and that can't be an adequate description of the world because the world is still growing. We're growing slower in Germany than we were 20 years ago, but we're also growing more slowly in America than we were 20 years ago. China is growing faster than it was 20 years ago, but it's also slowed down. So these many things are happening. How do we extend Solow to make it work? We have to think about technical progress. We'll do it very simply for you, but if you like this, take more advanced courses, go to graduate school, get a PhD. It's really interesting stuff. Robert Lucas, the famous Robert Lucas said, this is what keeps people up at night. This is what occupies his complete attention, because we're talking about, recently we've seen that China has become very wealthy compared to what it was when I was a kid. How do you explain that, right? How do you explain that dynamic? Okay. So Solow basically said, well, I see this is not enough. And Solow said this back in 1956. And he said, well, maybe the fact is that we need to consider technical progress, change in A, the position of the production function, because it could shift. And Solow said it's probably shifting in a certain way, in a systematic way. And again, Solow got the Nobel Prize for thinking very hard about this. And one of his insights was exactly that. The production function is shifting for many different reasons. We're more productive. Every period we're more productive. And we don't really understand why. It's not because I work harder that we're more productive, because even if I work harder, I can't make the technology work for me. The technology is in my hands, but I can't change it. If I want to change it, I have to put a lot of scientists on it and wait for 10 years before we can make hydrogen out of water, right? And Solow said, I'm not going to try to explain that. I'm going to call it exogenous. I'm going to say it's exogenous beyond the purview of the model. Again, economists are supposed to be good at this. What can't I explain? What don't I want to explain? What am I too embarrassed to try to explain? I put it in a corner, call it exogenous. Right? So that's what Solow did. Solow said, okay, can I extend this model to have an exogenous component of technical progress that makes labor more productive? So this is a special type, and I'll give you all three different versions of this because it's important. I learned it when I was in graduate school. I wish I had learned it when I was an undergraduate. Okay? Because it's about A. A is this stuff that just shifts the production function. The question is, how does it shift it? And there are many ways, but I'm going to talk about three ways. One is a parallel shift of the isoquant, or the production function shifts in a way that makes both factors equally productive, or makes them more productive. And then you can think about two different types of biased technical change that favors one or the other factor. And one we call Solow neutral technical change, which means that it makes capital more productive. So think about Airbnb. Okay, so I just went on vacation, I stayed in a house. That house was not being used. Now it's part of the Florida GDP. Its usage has generated GDP for the guy who owns the house. That capital became more productive. Ceteris paribus. All things equal. Okay? But the more relevant one for us is what we call Herod neutral technical change, which means that a person becomes more effective for whatever reasons that are exogenous just by virtue of that person working. So you use Word for a couple of years and you become more productive because you learn how to use it. Maybe it's learning by doing. Maybe it's just we develop new ways of connecting the dots and making the software work for us. Maybe we learn how to use a shovel properly. All these things it seems to be this inexorable improvement in the way we do stuff. And it seems to benefit labor more. It's called Herod neutral technical progress. So we can use an isoquant to think about this. Remember an isoquant? If I want to produce 100 units of GDP, what combinations of capital and labor can I put into this to get this 100 units? A lot of times you might say, well, I don't think there's any trade-off. I think it looks like this. But that's an isoquant too. It's a Leontief isoquant with no substitution. But generally we think, if you're thinking about GDP as a general good, okay, there are ways to substitute capital and labor. You can put more labor into the mix and less capital, or more capital and less labor. Okay, in that case, you can think about technical progress as a way that technology changes the marginal rate of substitution between capital and labor, because the marginal rate of substitution is exactly the slope of that isoquant. So you should write that down. The slope of the isoquant is exactly the rate of trade-off holding output constant. It's called the marginal rate of substitution. It's the ratio of the partial derivatives. Wow. You thought you'd learned that once enough, but it comes back again. Okay? So the question, of course, is what happens if technological change occurs Does it affect, what does it do? Well, technological change, if it's an improvement, means that the isoquant shifts inward because we can produce the same output with less capital and less labor. That's the definition of technological progress. The same output with less capital, less labor, the isoquant has to shift in. And the question is, how does it shift? Does it shift in an unbiased way, or does it kind of tilt one way or the other? Okay, so you can think about this one. Something looks like it happened. You might think about it shifting in the other way, right? And the question is, what happens to those two relative marginal products to make that slope go up or down? If the slope of that isoquant is unchanged, then we talk about unbiased technical progress. Now, it turns out that the way that Solow came down on this was he said most of technical progress since we've been measuring data is that it's labor augmenting. Okay? So we want to think about labor as being expanded by this term A as if, you know, two Professor Burdas here would be standing and giving lectures simultaneously or in different lecture halls. Okay, I just become more effective just by virtue of my existence. Okay? So we talk about efficiency units of labor. Now, Solow's genius was to say this is enough to save my model. I can generate economic growth in my model, even though labor is growing at a rate n and output per capita otherwise would be not growing at all. Okay, so he's able to fix this. So how does he do this? He said, okay, we're just going to assume that this A grows at an exponential rate. So think of Euler's constant times A0, which is the initial condition, and then you raise Euler's constant to AT. T is time. So as T goes from 1 to 2, we have exponential growth at rate A. Continuous This is enough to do it, because we can divide everything by A times L. Instead of dividing it by L, we divide by A times L. So everything is measured in terms of efficiency units. It's not just in terms of labor, it's effective labor. So Solow did this in 1956, and we're still doing it today. It's a pretty clever trick. Okay? So now we have an intensive form where you divide everything by A times L. A is growing at this exponential rate. We're not going to put a subscript on it, but it's growing. But it's growing for everything. So capital per effective unit of labor. The labor input normalizes to 1. So it's all a function of capital per effective unit of labor. Economic progress is going to be, and economic prosperity is a function of that. So the analysis of the Solow model is unchanged. Everything I just showed you still goes through with the modification. Now we're talking about per effective unit of labor. Per effective unit of labor. Okay, so we have the same picture as before. We can do the same analysis. So let me just remind you that now we have economic growth because in the steady state, output per capita will grow at the rate of technical progress. So we've got this result that we want. We have economic growth. We also have the role of capital formation. It's still important. So to get rich, you need to have technology growing. If the world is sharing their technology with everybody and we all have the same production function, it shouldn't matter. But in fact, it must matter. I'll show you that at the end of the lecture. That's the problem with European integration, is that some countries are backward and may never catch on. And that's why Europe needs to get into action and try to help those backward regions of Europe use the same production technology as we do. So let's look at those predictions. The Solow model is useful for us because it predicts long-run growth. It also depends that the long-run levels will be different of comparable countries. And it depends on the savings rate. Richer countries are ones that save more, ceteris paribus. Richer countries are ones that have higher rates of growth of technical progress. And if you have lots of depreciation, not so good. Why? Why is it kind of a disadvantage to have a high depreciation rate? You have to produce to accumulate, and you have to save more to replace the stuff that's burnt out. Ceteris paribus, if you have a low savings rate, you're going to have less GDP per capita. So imagine a world where we had to replace our computers every year. Imagine we were all working in a sector that required computers. We'd have to generate much more value added per capita just to take care of that business. We wouldn't be able to enjoy those computers in terms of consumption. That's a general lesson. Okay? Thank goodness a lot of what we have as capital is buildings, highways. The depreciation rate is lower. Okay? Population growth rate. If you're in a country in Africa where you have a very high indigenous growing population, this is a problem. Okay? So you have this extra hurdle to surpass. That's why a lot of what economists deal with now is trying to figure out, is there any way we can make population growth endogenous in our models in reality, because getting population growth down is one way to achieve prosperity for living generations. Of course, we know that one reason population growth is high is to replace children that may fall ill because of indigenous disease. So increasing aid to conquer diseases like worms and other things could be a great starting point. Again, growth economists love this kind of stuff. Growth will depend on A. Okay, so despite my song and dance routine, capital accumulation in the long run has to be driven by the technological progress term. It's all about technical progress. And I don't think that guy's going to be able to get out. You may have to go around. Sorry about that. I don't know why they have a door here, right? It's kind of crazy. A door that doesn't open. We'll figure that out someday. All right, so in a world without any technical progress, we're kind of stuck. But if we have technical progress, we have per capita increases. And we do observe that, but you see how important it is to understand the little a. So the attention of the world, and especially the economic world, is what determines A. And we know throughout the world, A is declining. Okay, so in the 1970s and 80s, A was about maybe 1.5%. Now it looks more like 0.5% per year. Okay, so the potential seems to be slowing down. We also see that there is growth that's associated with capital formation on the path to the new steady state. Okay, and it turns out that this is a very interesting fact, that basically along that path, within regions, for example, in the United States, or within Europe, or within the prefectures of Japan, this rate of growth, this rate of convergence is very slow, about 2 to 3% per year. Okay, so that means if I'm up here and you're down here, we're going to be converging at a rate of 2%, 3% per year. Now, how long will it take? How long will it take for that to be half of what it started? This is another McKinsey technique that you'll learn. You'll never forget it, because you'll probably never forget me. So how do you figure this out? Yeah. Yeah, you divide the 70 by the growth rate. It's called the rule of 70. Anything that's growing exponentially, you can't just say, oh, that's easy. I'll just multiply by the number of years. No, it grows on the growth. That's what cumulative exponential growth means. It's the same for shrinkage. So to get the half-life of uranium, you just need that rate and divide it into 70, and that'll give you how long you're going to have to wait till half of it is gone. Okay? It's called the rule of 70. This is on the exam for sure. I'll give you an application of this. Right? So if China is growing at 10% per year, which it was until recently, how long does it take for the GDP of China to double? Anybody? 10% per year. 7 years. Right. 70 divided by 10. Okay? So it's pretty easy. And you're going to say, this sounds like a strange rule. Well, go figure it out yourself. Take the log of 2 and see what it looks like. Okay? and then figure out what exponential growth means, because it means growth feeds on itself. So it's always going to, that's why hyperinflations are so unnerving, because if you have 50% increase in prices per month, prices get really high very quickly. Even if you have 50% per year, prices get high very quickly. Okay, so let's look at some data. Let's try to establish the empirical validity of what I've been talking about. So one of the things that I mentioned is this 2% rule, and this comes from empirics. So we have lots of data. We have 180 plus countries in the Penn World Table. We can look at those going back to the 1960s and try to figure out what seems to make countries grow faster. Okay, it's not easy. It's easier to take a single country where the rules of the game are the same and see what happens within that country. So you have the United States as a great example. The United States, lots of states, lots of little tiny regions, if you like. One would say countries. And they're all kind of dealing with each other, but maybe not. Maybe they're kind of autarkic. So Barrow and Salih Martin said, well, let's just pretend like they are autarks. How are they growing? Okay, and they looked at data since 1880. That's a long time ago, after the Civil War in the United States, when a lot of dispersion increased because a lot of the southern states were pretty much destroyed and had to start at a very low initial condition. So this model tells us something about that. It says that it's going to take a long time to close the gap if those regions of the United States look like the Solow model individually. So this is the first picture that impressed the heck out of me. This is the United States growth between 1880 and 1990. It's quite a long time, more than 100 years. And on the horizontal, we have the initial condition. So how much of what was GDP or income per capita in 1880? Okay, and we'll take the log of that because that, remember, changes in the logs. If the original variable is changing proportionally, then the change in the log is going to be linear. It's going to be a equidistant change. So he plots the South, the Midwest, East, and the West. The West was very rich in 1880, and the South was very poor because of the Civil War. What he has on the vertical is the growth rate after 1880. Okay, so you see the South grew faster, on average about 2.3% per annum faster. Okay, the West actually only grew at 1.2%. You think California, here I come. Well, in the 1880s, California was the richest game in town because of gold mining, because of other types of activity, and eventually later, maybe Hollywood. But all that doesn't seem to matter because the growth rate is lower. And what do you see in between? You see the industrial East and the agricultural Midwest. And again, they're all producing different types of output, but it's kind of GDP. And what matters is income, and that's what he's got here. So you see there seems to be a straight line there, pretty close. The slope of that line is about 0.02, or depending on how you measure it, 2 here because you're using a logarithmic scale. Okay, so that's kind of establishing this fundamental idea. And if you look at the data in the United States, you see that this convergence was very slow. It wasn't like all at once. And if you look at the individual states, you see that it's still pretty close, although there's some deviation from the line because states actually trade with each other. So the original idea of a autarkic Texas, Louisiana, Vermont is not valid, okay? So remember, the Solow model is an autark. They do it all themselves. But if you look at the regions of the United States, not bad. I mean, trade existed between the states, but probably not as much between the South and the West. In any case, it looks pretty interesting. The spread across the regions was shrinking, so it looks like convergence. It looks a little bit like the situation that I described. Now, if you look at Europe since 1950, since the end of World War II, you get a similar result, but you have to somehow control for the national identity. So each country has its own fixed effect. Those of you taking econometrics know what I'm talking about. basically, if you do that, you still get a negative relationship. This is a really interesting picture because it shows that even within Italy, some regions are growing much faster, okay? And those tend to be the regions in the south, even though people always say, the southern part of Italy is a mess. But in fact, it seems to obey, like every other country, this relationship. Now, the good news is that this works for Europe, but it doesn't work absolutely great because we saw already from the last lecture that since the financial crisis, things have gotten worse. So the poor countries in Europe have gotten poorer relative to the rich countries. So this seems to be a problem for the Solow model in its blind application. Convergence has kind of slowed down, if it hasn't been even reversed. So again, the big picture I'll give you in this course is that you've also got labor mobility, you've got capital mobility, and you've got trade. These are other things that we need to worry about to understand convergence. But the point is, convergence does seem to be occurring, and it occurred between East and West Germany. So one of my favorite research areas was looking at East Germany after unification because it's kind of the same thing. East Germany had a very low capital-labor ratio. West Germany was very wealthy and had a high capital-labor ratio. You pull the wall down, you let the countries interact. Well, suppose that they didn't interact at all, okay? Well, Professor Barrow, who is the father of this 2% rule, he said it's going to take forever. He wrote in the Wall Street Journal that it would take about 35 years using the rule of 70 and using his results for the United States. He said it would take a long time for East Germany just to close half of the gap. Because at the beginning, when the wall came down, the gap between East and West was 70% at the most optimistic estimates. Okay, so that's quite, so again, think of what is the most obvious next application of this idea? Think of the world, not Europe. Where do we have two regions, same language, same culture, very different initial conditions? Yeah. Right, Korea. So this is like we're all like drooling, I can't wait till this happens. May never happen, but if it did happen, we know that North Korea would need a lot of capital to get close to looking like South Korea. And where's that stuff going to come from? We're talking like $7 trillion US. That's a lot of dough, and it's going to have to be the international capital markets. It's not going to be South Korea. South Koreans, do I want to defer consumption for the next 50 years so these guys can look like me? I don't know, right? So Barrow said it's going to take a long time, but Barrow wasn't quite right because the first 10 years, East Germany did jump quite a bit. And we can talk about that maybe later in the course. We think that has to do with the adoption of Western technology and Western methods, and also just infrastructure. But East Germans and West Germans had the same education, everything else. The production functions could have been the same. Since 2000, Barrow is on target. It is taking a longer than we thought. Okay, so again, we need to think about this convergence along the adjustment path because this is the formula that Robert Barrow and Javier Sala Martin derived back in 1990-91. And this is basically explaining the rule of 70 by trying to figure out what makes lambda. Lambda is this rate of convergence. Lambda multiplies the distance of y star from y. Y is where we are. Y star is where we're going as a function in relation to y star. And it turns out they show in a Solow model that it's got this neat formula. It's just basically 1 minus the capital elasticity of the production function times the slope of this capital widening line. Okay? So we can actually just plug in some values and see what happens. Right? We can, and if you're interested, I can post the derivation. It's a little bit messy, but we did it in Macro 1. It's a Taylor approximation of the behavior of the Solow growth model around the steady state. So it's kind of an approximation. Well, it turns out if you take, what do you think alpha is? What's a good value for alpha? You may have seen it. The capital elasticity, or in a competitive economy, the share of capital of GDP. Any guesses? Okay, so a third is a good guess. The ballpark estimate for industrial countries is like a third. Some might say in Germany maybe it's a bit more. America might be a little bit less. What about delta? Again, we're talking about the whole capital stock, not just your computer, but the aggregate of computers, buildings, highways. %, maybe? 5% per year, maybe 4%. Population growth we can figure out. That's in the US it's like 1%. Germany it's maybe 0.5%. So we can plug in numbers and see what this lambda, this convergence rate is. Okay, so a lot of people have done that. If you do that just blindly, you get a number that's too big. The economies are converging much more slowly. So even Burda said this is way too high. It's like a number like 0.5, 0.05, 5% per year. That's way too high. Okay, so the trick, you might say, well, maybe we can take this alpha and make it a bit larger by saying that part of the labor input is actually human capital, people's knowledge, which is like capital. You're investing in your human capital right now. And that depreciates at a certain rate. So there are many papers that have tried to look at this. You get a better result. So we can actually get close to accounting for that. It's kind of interesting. So, we're chasing this number that explains convergence for countries that are separated. Well, we want to do better than that because we want to explain European integration. You got capital mobility. Finland can send its capital directly, doesn't have to save anything, they just send it over there. Or maybe some other country could send it over, or some laborers leave Finland, raise the capital labor ratio, leave Poland, raise the capital labor ratio in Poland, or they start trading. Okay, so we still need to think about this convergence. I'm going to call this beta convergence. This is what Burda called it. Professor Burda called it the beta convergence. But that assumes everything is smooth and converging at some steady rate. But in fact, we have things like corona, we have earthquakes, we have financial crises. They tend to move us around. So we have, if you look at the United States, the picture I showed you before, the picture I'll show you right now, you have these shocks. They may push you away from where you were going before. And if you have that, you still might have convergence, but occasionally you have these shocks, these disturbances that may hit your region. A good example would be an earthquake in Portugal. Bad news, right? Or a drought in France, or a financial crisis in Italy. Or German unification. That was a shock for Germany because the Germans had to pay for that, right? So we call that sigma convergence. So these are the United States regions. You can see this. The U.S. South had a bit of a setback in the 1930s. The East had a setback after World War II. Overall, this kind of gives us the impression that dispersion of personal income is declining, and sigma is the standard deviation symbol. That's where it comes from. That standard deviation will always be positive because we're always going to have these shocks, but it's going to get tighter. So that's a more optimistic view of Europe, right? Maybe Europe will always have its shocks, and we'll never see Bulgarian GDP look like German GDP, but it'll be pretty close, getting closer, and occasionally there'll be some shocks. Okay? So this points to the central difficulty of the Solow model. So what you should take with you today as a little lesson is that we have a problem. We have a problem with the Solow model. The Solow model, it kind of assumes that we all have the same production technology. We have the same way of making capital and labor produce output. And if you go to Albania is in Europe. It's a fantastically interesting country, has a huge history, but you have to be Albanian to understand it. A lot of it's linked back to Turkey, and a lot of it is not, and then you've got Serbia and all that stuff. So this is a very unique history. Well, another way of thinking about this is every country has its unique history and institutions that condition its production function. So it's not just about technology. It's not just about how I put this bolt in this hole and turn it and make something. It's also how do I get along with my neighbors? How do I run my society? Do I have a police that functions, or is it completely corrupt? Do I have ethnic strife? Do I have problems dealing with my neighbors, just can't deal with them? Are there cultural reasons? Is the weather okay? If you live in southern Spain, it's really hard to work in the summer. It's really hot. That reduces your ability to put capital and labor together to produce something. Maybe you can produce lots of oranges, but not much more. And you got to go out and do the oranges. You got to pick them. Human beings need to run the machines. So we economists now think in terms of conditional convergence. Conditional means conditioned on or assuming a certain production function. So we have a huge degree of freedom now. We can assume anything we want, but that's not true. You're going to only have convergence if the production functions are approximately the same. Remember I told you about France and Germany at the beginning? France and Germany is a wonderful example of conditional and unconditional convergence, because Germany and France really look similar if you look at all the different dimensions over the past 50 years. It's an amazing story. Same thing is true for Belgium, the Netherlands, Luxembourg, one might say Switzerland, and increasingly countries like Poland, Estonia, Lithuania, Latvia. So, in a sense, we could probably say the European tradition, the European rule of law kind of governs the way economic systems are working. And that's going to condition the shape and the position of the production function. So to do this properly, either we say Europe and European integration is kind of a project of having the same production function, and if not, the EU has to make sure that those conditions are the same. And that's one way of understanding the chapters of the European Charter. We want to have the same conditions of enterprise, state aid, access to markets, freedom to do your profession the way you learned how to do it at home, and to start a business. Harmonizing that is one way of getting the same production function. So the lesson here is that if you don't have it, you're going to have different places to grow to. So this is from my textbook. Left-hand side, a productive country, a different production function from the right-hand side. And if you put the same Solow households in both of those economies, they're going to have different GDPs per capita. Because if you're saving a lot, but you have a very unproductive economic system, it's not going to help much. And when I say unproductive, I mean, it could be that just people are robbing you. People come by and just take your property. That's part of it. Or you start a business and someone just takes it away from you. That type of uncertainty is not good for economic activity. Or if the weather's really hot, or if it's super cold, or if, there are all sorts of other reasons that these production functions might have different levels. So we economists are really interested in trying to understand why they're different. So if you try to use this approach to think about Africa, or think about Latin America, or Asia, you can get much farther because you can understand that, for example, Honduras and Korea had the same GDP per capita in 1960, and now Korea off the map, Honduras plunking along. And it has to do with all the things I just discussed, including human capital. So the genius of South Korea was investing in education, right? And moving the production function, holding everything else constant, moving it up. Okay? If we don't do that in Europe, we're in trouble. So this is my last slide. If we're not able to fix this, we have an issue. Because if we have permanent differences in TFP, that means that Finland and Poland have different production functions, and the efficient allocation is no longer the diagonal. Where is it? Where's the efficient? if we know that Finland has a more productive production function than Poland, yeah.
Wouldn't it then be efficient for all the labor and all the capital to be in Finland?
Bingo, exactly. Right? So you end up, you turn the vacuum cleaner on and just suck everything out of Poland and put it in Finland. Sounds absurd, right? That's the implication of the model. And you could take the GDP you generated and give it to all the people who've migrated, and everyone would be better off. It's a more efficient outcome. So there must be something else holding these people back, and that's what we're going to learn about later on in this course. But that's the dismal prediction if these two regions have a different production function. The diagonal is no longer the set of efficient conditions. Yeah.
But if we have a concave production function, and Finland has a slightly more productive or more efficient production function than Poland, would it then be efficient to just let Finland produce slightly more?
Unfortunately, no, because if you look at this means that basically, no matter how we slice it, it always makes sense to put more people into Finland because their production function for any capital labor ratio is higher. Okay? So unless there's some friction, like maybe congestion, maybe Finland gets so full of people that the people go crazy and they say, we don't have any housing for these people, no public spaces. There are all sorts of things that we could argue would keep us away from that dismal looking point here. Okay, but that's what we're looking at. Okay, so again, it's the logic of this frictionless place. It's just an efficiency statement. It's not. I'm not saying this is a good thing, but this is one way of understanding the dilemma of cities. One of the biggest problems in world development today is that cities are getting bigger and bigger. And why are they getting bigger? The population is not getting bigger. It's people are leaving the countryside and going and they're not just going into little cities, they're going into the big cities, right? And unless we develop ways to make it more interesting for people to stay where they are, maybe, and reduce the congestion that we have in mega cities of the world today, we're going to have some trouble. So the rest of the course, we'll be thinking about ways to avoid this outcome. And I think one interpretation of today's lecture is that European integration in the first instance means, okay, you can integrate with us, but you have to have our institutions, you have to have our rules of law, and we have, in a sense, we get to give you all the technology, and we can build the factories in Albania using German technology, right? Not necessarily using German capital, but using the state of the art. And therefore, the people in Albania can help achieve the efficient outcome staying there. Okay, that's one way to think. Or, I told you already, we have trade. So the rest of the first part of this course is understanding all these very, very interesting things, which are kind of ultimately, to me, a justification for the EU. The EU is establishing a common set of laws and rules, a level playing field to make it all happen. Okay? It's a pessimistic note, to end on because, I don't know, 2% per year is pretty slow. I think we can do better than that. And I think if we look at what's happened between Germany and Poland in the past 30 years, it's pretty impressive. And I hope we can make this happen with our trip because it would be fun. In fact, we'll try to go to this place that's right on the border so you can actually just spend half of the day in one part and then go to the other. Don't forget to bring your passports, even though they're not checking these days. Okay, so I was kind of quick today, but it was fun. And the Solow model should be familiar to you. Berfin will talk about it in section. These are the key concepts you want to remember. Don't forget the 2% rule and the doubling rule for exponential growth, or the half-life rule for shrinking things, and the rule of 70. And I'll see you next week. We'll talk about capital mobility.